Fantastic to be here. Had the pleasure of talking on a similar topic at this conference this time last year. And I guess we have the third day, so it's fantastic we've got people in the audience. Normally that's always a challenge, so a bit of a testimony to the fact that this topic has some interest. And I think just reflecting on the last 12 months, it is actually phenomenal. The expansion in the ecosystem that is supporting quantum technology, the developments specifically in post-quantum cryptography, and the investment behind it, and the general information that's available now is extraordinary. So it is a fast-growing, very relevant, industry and far-reaching technology, which hopefully we'll explore today. I just wanted to reflect that, of course, Hollywood, in no short measure, has managed to capture our emotion and heart on all things around quantum physics, from the multiverse, three-body problem, the dark matter and the Spider-Verse and so forth and so on, which is fabulous in terms of getting people behind and excited about what quantum physics is and how can we apply it. But I guess in this session we're looking to sort of take it back down to earth, so to speak, and look at some of the realities of what quantum physics is doing, and particularly quantum technology in relation to post-quantum cryptography and potentially even quantum key distribution, an application of quantum computing with quantum physics. So to put some context in this, obviously, as many of you will be aware, we're already leveraging some of the brilliant work that Werner Heisenberg, originated in his paper in 1925 on quantum physics in things that apply to us every day, or almost every day, such as when we go have an MRI scan, when we're walking with our iWatch and leveraging an atomic clock to manage our steps, when we're developing up supercomputers with semiconductor technology, and really, really importantly, how we're leveraging some of the phenomenal material characteristics of semiconductive materials as a platform for quantum technology. And that, in no short measure, has changed the nature of our ability to start to leverage and simulate what is happening at an atomic scale or a subatomic scale into a technology we can harness. So just to reflect, and I'm sure many people are very expert in either quantum computing or obviously cybersecurity here, but I thought just to reflect on a couple of relevant points and what the noise is all about. Obviously with the developments in artificial intelligence, that range from deep learning to neural net and so forth, machine learning, as well as automation, broad-scale automation, simulation, and this at scale and permeating most operations now, or looking to permeate most operations from finance to public sector, government, defence, critical infrastructure and industry. By solving one problem, we're creating another. Obviously, the currency of these industries now is data. And of course, there are many malignant actors or bad actors out there looking to take advantage of that data. And some of the challenges today are that, in fact, data is being harvested now under the premise that at a later date, that data, once quantum computers take hold, will be able to corrupt that encryption or decode that encryption and leverage that data. So it's a genuine problem now, and it's really almost an existential risk we are facing. And that's because of the power of quantum computing. Shor, who was one of the great, theorists in developing quantum algorithms through the quantum information era of the 80s and so forth, developed up what's called the Shor algorithm. And as many of you would realise, one of the key encryption technologies relating to asymmetric or symmetric technology in terms of the sum of two very, very large prime numbers and factoring those into the prime divisibility of prime numbers themselves is a very, very, very difficult thing to do, and in fact a theoretically or infeasible thing to do in conventional binary serial processing. The Shor algorithm in theory enabled this to happen, and in fact can be embedded into a quantum infrastructure and render that encryption unencrypted within seconds. So these things are real grovers as well in relation to asymmetric, and then the hashtag itself in terms of the BHT algorithm that could potentially also replicate the hashtag. So across the spectrum of all of the encryption we use, there is a real potential for quantum technology and quantum capabilities that operate in the very, very massive if you like, complex, multidimensional, multi-parametric super-polynomial space, solving many problems simultaneously, to actually start to undermine our encryption technology. So things need to be done, of course. The other point is not just in terms of changing and ratifying and making more hardened our encryption technology and creating a program of transition to that, is ensuring that we have a cryptographic bill of materials to support that. Just like a software bill of materials or a hardware bill of materials, our CISO needs to also think about how we manage our crypto capabilities and software and inventory, currency of cryptographic standards and so forth, as well as the methods about which we're ensuring cryptographic protection constantly. So this is a case of monitoring, managing, understanding non-conformance, putting in programs of change and so forth. A governance element, which is critical. And I think most companies now are looking at this or have embarked on programs of this nature, particularly in cryptographic standards, in lieu of post-cryptographic challenges. If not, there are many technology houses out there as well that are really enabling the platforming of automated post-cryptographic standards and quantum-safe cryptography in an automated fashion, from obviously the likes of Microsoft, IBM, Azure, Amazon, etc., that are really starting to enable the ability for the CBOM to run in an automated fashion and also start to support, with all of the necessary technologies, the introduction of a CBOM. So these are all very important things, hardening the encryption techniques, which we'll talk about later, as well as the CBOM itself, an operational management system to support the active management and governance of your cyber security estate. But firstly, I just wanted to, and look, I don't know in the audience the maturity of everyone in the context, or knowledge, sorry, not maturity, of quantum physics or quantum technology or quantum, I guess the combination of those two. But I thought it worthwhile just to perhaps step back a little bit and try to discover really why is this technology so profound? What is it about the quantum space? What is it about quantum mechanics that is so fundamentally different to our classical mechanics? If we think about our classical world of Newtonian physics, it operates in these legato sort of analogues and waves, vectors, and we think about the world in the context of gravity and I guess space-time, and we observe all of these fundamentals of space-time in the context of gravity because we exist and we have mass. In the world of quantum mechanics, this is fundamentally different. And this started out in 1911 with Rutherford, who developed and understood the nucleus of the atom and that there are electrons around the atom, and Niels Bohr determined that in fact these electrons weren't really zipping around this atom like a solar system, but in fact had these energy states. And it was noted that in fact similar to light that operates, or photons that operate as quanta, discrete packets, so do all subatomic particles, from electrons to photons to bosons to fermions to leptons, etc. All operate in a discrete manner, not in this analog manner. So a very fundamentally different paradigm about which they operate. So that's one point. The second point is, then came along Heisenberg, Schrödinger, Born, all people perhaps you've heard about, physicists of the 1920s, that said actually forget about trying to think about the way that electrons move and work, throw that away, and actually just try to understand the observations we're making about the way that light is emitted, the way that it is absorbed, and how that relates our ability to predict where electrons are. And in fact, that got formalised in both Heisenberg's matrices, Schrödinger's wave equation, and Max Born's amplitude probability, that basically said, hang on, it's not a case of electrons here or an electron's here or it's moving there. An electron, in fact, is in many, many states simultaneously, energy states. And in fact, an almost infinite number of energy states simultaneously. So if we can start to model and understand these energy states and this enormous energy space, if you like, we can encode that and understand that through mathematics, bring that into a platform that can simulate that, and then harvest that through I guess, software and innovation. Imagine what we can create as a computational space to solve very, very complex problems. Because instead of serially working through and trying to simulate this from a binary perspective, we have an almost infinite number of options of where these problems are, or where this energy state is, that we can simulate as a problem set and solve simultaneously. And that notion is superposition, which is a fundamental characteristic. In other words, an electron can operate at an energy state of 0, for example, or 1, or any infinite number, or near infinite number of 0 and 1, which is a very difficult thing to consider. But if you imagine a dimmer switch, and the dimmer switch is off, you turn the dimmer switch on, it has a range or a spectrum that reaches until it's fully on. So we can simulate or think about an electron in that regard, or a photon, or any subatomic particle. And that gives us a huge space to work with of possible outcomes. And so it was determined that there was a probabilistic set of outcomes we could work with that could simultaneously solve and manage, if only we can platform that. There is a challenge to that. It's called decoherence. In other words, to maintain superposition, this state where we can observe all of these energy states of an electron, we can codify that into our mathematics and our software and our quantum technology, we need to maintain it in a coherent state, which is very, very difficult because it needs to be without any disturbance in energy or noise and not to be observed. One of the fundamentals of the Heisenberg uncertainty principle is that when you observe a system, it collapses out of a quantum state, this state of superposition, into a classical Newtonian, or our classical state that we see, back to knowing where something is in space and time, which is a fundamentally different paradigm. And we don't get that optionality of this very, very large problem space to work with. So we have to maintain superposition and coherence. The other very interesting characteristic of this, according to quantum theory, and that actually has been proven through some experiments in China, is this notion of entanglement, which is, as Einstein said, is the spookiest property of them all. And that means that one electron can not only be in superposition, having literally simultaneously all of these energy states, typically known as spin up, spin down, etc., 0, 1, or any number of 0 and 1s, but it can also work together with another electron. And so if you've got two electrons working together in superposition and measuring each other, or you've got 4 or 16 or 32 electrons all in superposition, all working as a system, the exponential increase of that is significant in terms of the number of options of solving complex problems, or translating that into a problem set to solve, becomes very, very exponential very, very quickly. So to give you a sense, combining all of these features, if we can harness that, provides us with an enormously large opportunity to solve very, very, very complex problems that are previously infeasible. The last critical point of this is that, in fact, the same time that the nucleus was being discovered from Rutherford, a Dutch physicist called Onnes also was experimenting with helium and mercury and cooled mercury down to almost 0 degrees Kelvin, roughly about minus 274 degrees Celsius, and noticed some very, very, very strange behaviour. And that's called superconductivity, which is literally a fourth state, a whole different domain about the way that properties of materials work. So not just a gas, not just a liquid, not just a solid, but a superconductive material. And two classic properties of superconducting materials are that, one, magnetic fields can't pass through it. So hence trains leverage superconductivity to reduce friction, and you have superfast trains. The other one is that there is zero resistivity in these materials, which is a very interesting property because you don't need a power source to create a voltage to move electrons, which typically want to repel each other because they're negatively charged, but actually work together. And they're mediated through positive charge through the way that the lattice of metal operates at a superconductive state, and it mediates the positive charge with these electrons, their negative charge, and enables them to stay together as pairs and, in fact, move through material with zero resistance. Now, that's a really interesting proposition because the only other thing that doesn't need a battery source or a power source to apply voltage is an atom. You've got electrons moving around a positively charged nucleus and maintaining that state with zero resistance. So that was quite an interesting proposition to say, well, look, hang on, this superconductor material kind of works the same as an atom in terms of the way the electrons work, zero resistivity, and this balance between positive and negative. Now, the other interesting facet that came from that was the BCS theory that determined how molecularly this worked. And this is really important because electrons started to form these pairs in superconductive material called Cooper pairs. And by virtue of those pairs, they could not just operate in superposition, but they were entangled. So we were able to look at superconductive materials and metals and think, how do we make that the foundational material of quantum computers? Because we have electrons in superposition that are entangled, and in fact, in 1 gram of aluminium, for example, we have trillions of electrons that we can start to work with. And if we can do that, and if we can understand the wave functions through Schrödinger's equation, we can have many wave functions. We can then work with all of these different wave functions to cancel things out that aren't relevant, highlight and amplify areas of a problem that we really want to focus on within that wave function, and then solve that problem through quantum algorithms such as Shor algorithm and so forth. So it's fundamentally different. And the other important part is that electrons can pass through insulating materials, and this is a very important part that I'll talk about shortly. So, to finish the story, Felix Bloch was a great, solid-state physicist of the 1940s. He developed a lot of nuclear magnetic resonance technology and capability and algorithms. It was leveraged in the 80s, and this model of a qubit came about, which is the fundamental 1, 0, or 1 and 0 model that we use in quantum computing today. David Deutsch came up with this notion of a quantum Turing machine to validate the theoretical possibility of quantum computing working, similar to any other Turing machine. It simulates and models each of them to actually simulate each other in a pair, and then was born the qubit, and the quantum technology came from there. As I said, the other important part are gates, Josephson gates, which are insulating membranes, if you like, that we introduce in quantum chips that enable these tunneling pairs or pairs of Cooper electrons to tunnel through these gates. And by shooting microwave photons at these electrons, we can change their amplitude, their position, etc., where they sit in the wave function. We can also change the voltage as they're passing through these gates to focus and modulate and change the areas of the wave function we're interested in, or many of those wave functions working together. And so we set up, similar to any software system or hardware system, logic control through there by operating through Josephson gates and allowing these Cooper pairs to work through those gates in superposition, etc., and enabling a greater level of coherence because we're operating in a superconductive material. Now, the last, bastion and challenge we have is what's called error correction. And error correction is really one of the most challenging areas at the moment because not only do we have to maintain electrons or photons in coherence, in other words, in superposition, we have to also ensure that as we're modulating all of these, if you like, Cooper pairs, going through all of these gates, that we get a clean signal at the end of this quantum information as it passes through these processing units, which is a very difficult thing when you have thousands and thousands of these gates and thousands of these qubits and thousands of these quantum chips in theory, and solving very, very complex problems. So what the development now is, and looking to hopefully be sort of managed, solved by 2030 to 2033, is quantum error correction. In other words, once you have a dirty signal, you can fill and backfill that signal to make it clean again. And the interesting story behind this is the notion of Mandalorian black hole theory, and wormholes, where Mandalorian is an Italian physicist who's developed up some very clever mathematics to observe the surface features of the entrance to black holes, the event horizon and so forth, and wormholes, and infer literally what is happening from the areas in 3 dimensions within, or 4 dimensions, or string theory, whatever you want to go to, within these black holes. It's very far-reaching mathematics, but the point of that is if it is looked to being applied, it's called surface code or gross code, looking to be applied to these signals, this quantum information that's created through these gates, because we've got areas that have been corrupted or they're full of errors, but we can use this surface code to fill in the missing information. So that's really a great development that's been happening very recently in the last 12 months and ongoing, and looking to develop what's called quantum error correction by around 2033. So that brings us to what we're really talking about, which is this quantum stack, which actually, interestingly, looks pretty similar to most computing stacks. So in no short measure, quantum technology really does stand on the shoulders of giants in the I guess, computer space. The developments in the chip technology and the developments in hardware and scale of hardware and ability to mesh hardware together is being leveraged very heavily across quantum technology. And so, of course, you have a user environment, you have a software environment, you have how to encode that software into the language of the hardware, you have the hardware itself and all the material sciences and quantum physics that operate in the semiconductor state. And this thing is obviously a very, very complex array of technologies, from software to hardware and so forth. And I guess there's, again, leveraging a lot of generative AI to support the user, how to best manage and develop software, the same as OpenAI, ChatGPT, etc. Grok, we can all develop software now, we're all software engineers. The same, in theory, can be applied to quantum computing. There's a lot of work, and I'll show a roadmap of that happening shortly. So who's who? There's a lot of participants nowadays in quantum computing. There's obviously the major players from from Google, IBM, and Microsoft has released in Nature magazine an article around Majorana 1, which they've, I believe, theorised that they are accelerating much more rapidly towards quantum error correction. The Chinese government itself has harvested, if you like, all the current quantum technology that was within the private sector in China back into the state, and is looking at quantum computing as a fundamental, I guess, next generation technology that will really profoundly change and explore and invent. And then there's, of course, a significant value chain that support that quantum stack. And if you take that to the startups, there's a huge, rapidly emerging number of startups globally that are also looking to be funded through governments, through other private sector investment. So this industry is real. It is evolving very, very rapidly. And I guess the opportunity for change is profound. I'll give you an example from IBM, given that they're one of the few companies, I believe, that are actually servicing the full stack of that quantum technology stack. And I did work for IBM for some time as well. But as you can see from those numbers, this is real. Quantum computing is being used, and is being used for optimization across, for example, distributed energy resources with E.ON, are looking to best understand how to model the cost of operation, the cost of energy provision, their retail models, tariff optimization, renewable forecasting, putting all of that together, which is an incredibly complex constraint model, to best model their supply and demand and their cost versus their revenue across their entire estate. You've got many battery manufacturers, from Mitsubishi to Mercedes-Benz, looking to understand how they can model battery chemistry. Within the battery, that's a black box, effectively. So there's a lot of different applications that are being used, from agriculture, nitrogen fixing, simulating nitrogen fixing enzymes to better enable concentrated agriculture. It goes on. Anywhere that chemistry is applicable, anywhere that optimization is applicable, and particularly in cryptographic standards, the cryptographic key distribution, where it's looking to leverage photons in superposition and entangled. So the sender has a photon that is entangled with another photon through a fibre optic system. The receiver has that other entangled photon. Packets are sent in superposition. You can imagine they can be an enormous amount of data that's transmitted in that regard. And accordingly, if according to the Heisenberg uncertainty principle, if anyone observes that system, the system collapses to be a classical physical system. In so doing, as soon as someone looks to hack that system, the system is observed, it collapses, and it ceases to be in superposition, the entanglement fails, and of course you can detect that someone is trying to eavesdrop. And so it has this immutability. So as a roadmap, as I said, there's the usual suspects: data scientists, there's researchers, quantum physicists, also hardware and software innovators. And as I said, towards 2023, I think we're looking in the vicinity of somewhere upwards of 2,000 qubits and 1 billion gates. Currently, we're sitting with Heron, I think, at around 156 qubits of error-mitigated, not error-corrected, error-mitigated qubits running, and in the order of, I think, 7,500 gates. Fundamental change. I think one important point, now we're seeing the advent of actually workflows created between classical computing and quantum computing, which is, again, really bridging the gap towards error correction and changing the way that we can actually start to blend supercomputers such as the Riken computer in Tokyo with a quantum computer. And it's being applied very heavily now in pharmaceuticals and supramolecular interactions, in energy conformance around molecular modelling and so forth, to create and accelerate drug and pharmacology, and doing it at a much more efficient rate. In fact, I think typically reducing, I think 3 million labour hours down to about 3 seconds in theory, that they're starting to simulate in the lab of recreating these molecular capabilities. So back to quantum algorithm. I think I've got 5 more minutes. But so again, there is a lot of work being done. So if you think about all we've said, which is that we have this profound capability to now encode and simulate what's happening at a subatomic level, which exhibits these remarkably different attributes of, compared to classical states where we have a point and we have a momentum and we can chart the path of particles, of ourselves, of macro elements. In the quantum space, there is no such thing. In fact, every state is possible and is actually happening simultaneously, and enables us to use this broad set of energies to simulate in a quantum computer as a problem set. And so that's enabling us to think about how do we mitigate and harden some of these symmetric, asymmetric, and hashtag functions across the Shor, Grover, and BHT algorithms. And a lot of these are now being embedded in, and developed and actually really starting to accelerate from 12 months ago. The implementation, the development across the NIST, across the European Task Force, has been phenomenal. And so these are now really advancing in terms of adoption and being not just in a state of examination and pre-use, but now starting to be used accordingly across the lattice and the hashtag-based sort of capabilities that the Crystal and the Falcon and the Sphinx are starting to sort of support. So I guess the EU has also has embarked upon this with a task force that looking for an implementation roadmap up to 2026. There's a post-quantum cryptographic group that's set up through the NIS Cooperation Group, the National Institute of Science Cooperation Group. There's many developments around Cyclone DX, the Open Web Application Security Project, and so forth, all supporting the hardening, implementation, and validation of these post-cryptographic standards to ensure that once we get into a world of quantum technology and quantum utility, error-corrected quantum capability, that these quantum and cryptographic standards are immutable, in other words, cannot be decrypted by quantum technology. Again, an example roadmap shows, I think, what we've covered, which is the fact that there is ongoing development to automate, implement, I guess, a broad range of capabilities from generative AI, large language models, to help support the ongoing application and understanding of the best development, transition roadmaps, active monitoring systems, and looking to really start to support a broad end-to-end, top-bottom, horizontal capability of cryptographic immutability in a post-quantum cryptographic world. And IBM's a great example, again, of the quantum safe roadmap. So this is all public domain, so by all means, please go onto the websites, dig down into this and learn more. So just some takeaways. Look, as I said, the advancement in asymmetric, symmetric developments has been significant. and rapid over the last 12 months. I went through this 12 months ago, and these were still being considered and ranked, and now they are actually started to be implemented and used in many, I guess, large-scale infrastructures from a cryptographic point of view. Of course, your CISO needs to be on board. It doesn't have to be a fully automated, high investment. It just needs to be a good quality management system to maintain your inventory and your CBOM, your cryptographic bill of materials. But it does need to happen now because the advent of quantum computing and the ability to start to undermine existing quantum standards, as I said, through Shor, through Grover, through BHT, and the standard symmetric, asymmetric, and hashtags is real. And in fact, as I said, people are harvesting now to decrypt later. So we must act now and start to introduce these schemes. I'll leave you on a quick video. How do I start that? Just to perhaps put a face to a name, so to speak.
Introducing the IBM Quantum System 2, the world's first modular utility-scale quantum computer system. Quantum System 2 was designed to tackle complex problems that lie far beyond the reach of today's classical supercomputers. It stands 15 feet tall and operates in a near-perfect vacuum at temperatures colder than deep space. Initially powered by three 133-qubit Heron processors, Quantum System 2 is fully upgradable to the growing line of utility-scale QPUs that IBM will be releasing over the next 5 years. This is the world's first modular utility-scale quantum system. So in addition to talking about physical qubits, we now need to be concerned with circuit size. By the end of 2024, each of the three Heron processors in Quantum System 2 will be able to process a remarkable 5,000 operations in a single quantum circuit. But the real triumph of Quantum System 2 is its modular design. Our new quantum coupling technology will allow multiple Quantum System 2s to connect together to create systems capable of running 100 million operations in a single quantum circuit. Continuing down this path, we plan to realize a system capable of running 1 billion operations in a single quantum circuit by 2033. That's why we call Quantum System 2 the building block of quantum-centric supercomputing. Today, our clients and partners are already using our 100-plus qubit systems to advance science, surpassing brute force methods deployed on the world's most powerful classical supercomputers. And soon, they expect quantum applications offering unprecedented business value. Our mission is to bring useful quantum computing to the world, and it starts with Quantum System 2.
Okay, that was clearly a plug for IBM, but the point of that is that there are, of course, as I said, from that ecosystem slide, there are many companies embarking on this mission, and it's an important one. And from a cybersecurity standpoint, please, as I said, we need to start to move, otherwise this world's going to be a very different place if we don't. So thanks very much for your time, and really appreciate the audience. Thank you.